Hello, welcome to the Webcast. My name is Greg Jew, and I'm an application development engineer working on 5G applications at Keysight Technologies. So today there is increasing interest in utilizing the sub-6 GHz spectrum for new and emerging 5G applications, as well as potentially sharing spectrum between 5G and satellite applications in the 28 GHz frequency band. Spectrum sharing between radar and LTE applications is yet another area of interest. Operating in the crowded frequency spectrum poses questions as to how waveforms will interact and potentially interfere with each other, and how their coexistence might impact system performance. Researchers and engineers need flexibility in the R&D lab environment to evaluate many different potential coexistence scenarios before testing in the field with actual hardware. This webcast will discuss a flexible testbed which can be used to evaluate many potential coexistence scenarios for 5G, 4G, satellite, and radar applications. Several different scenarios will be examined and discussed in this presentation. We'll first discuss what is meant by sub-6 GHz coexistence and why it is a topic of interest for 5G applications. We'll then briefly introduce some of the candidate 5G waveforms being proposed for 5G applications and discuss why coexistence with 3G and 4G is important. We'll then show a flexible testbed being used to evaluate what-if scenarios in 3 different case studies. The first will be a case study showing coexistence with 5G candidate waveforms combined with 4G, 3G, and personal area network or PAN waveforms. We'll then switch gears and we'll move up to the 28 GHz frequency band. There is discussion about potentially sharing the 28 GHz frequency band between satellite and 5G applications. So we'll consider a case study in which we examine the coexistence of a 28 GHz satellite waveform with a candidate 5G waveform. We'll then move on to a radar and LTE coexistence case study where we'll evaluate the impact to LTE VM as well as simulated bit error rate or BER. Then lastly, we'll move back to 5G. We'll discuss millimeter wave applications, then conclude with a summary and a list of additional resources. What exactly is meant by the term coexistence? Well, one definition is to exist together or at the same time. Another definition is to live in peace with each other, especially as a matter of policy. As you can see, both of these definitions are relevant to today's topic. A glance at today's frequency allocations quickly reveals that today's spectrum is very crowded and complex. The demand for more data, in the absence of additional available spectrum, is resulting in proposals on how to use the available spectrum more efficiently. One is the proposed future spectrum sharing between radar and LTE. There are also other proposals on using LTE in the 5 GHz unlicensed band to use the unlicensed band as a secondary channel. Cognitive radio approaches might also be investigated for potential increased spectrum utilization with dynamic spectrum sharing. For this approach, dynamic spectrum access technologies might be used to find and occupy underutilized or white space spectrum on a secondary basis. Let's examine this in the next slide. Cognitive radio potentially improves spectrum utilization to a large degree through decentralized spectrum management. In some applications, the cognitive radio is operating in spectrum, maybe on a secondary basis, and is responsible for avoiding interference to the primary user. TV whitespace is one example. In this diagram, we can see that algorithms can be either reactive or maybe even predictive, as shown by the signal that splits into 2 frequency bands. Some of the 5G candidate waveforms utilize filtering on a per subcarrier basis or per subband basis to reduce out-of-band spectrum emissions. Improved out-of-band spectrum suppression can help to maximize the utilization of spectrum while minimizing interference with adjacent users. We'll discuss filtering approaches for some of the 5G candidate waveforms in the next section. Today for 5G, there is research in progress at many different frequencies with different bandwidths and many different proposed waveforms. Currently, there is not a defined standard for 5G waveforms, frequencies, or bandwidths. However, research is underway evaluating potential candidate 5G waveforms. So this poses a couple questions. If 5G waveforms will occupy sub-6 GHz spectrum, then how will these new waveforms coexist with existing legacy 3G and 4G waveforms? Will they be secondary or primary users of spectrum? How can potential interference effects be evaluated early in the R&D phase? Beyond 6 GHz, there's also interest in using centimeter waves and millimeter waves for 5G applications, which we'll also discuss. This is a simulation example showing a sub-6 GHz spectrum scenario with candidate 5G waveforms, FBMC, UFMC, and GFDM, combined with 3G and 4G waveforms, GSM, Edge, LTE, and WCMA. You can see that the out-of-band spectrum emissions of the candidate 5G waveforms are significantly lower. Note that these waveforms are simulated, so in effect they are ideal in this case, and the waveforms could look significantly different after being passed through hardware. So this is just one scenario, but there may be many different scenarios required to fully understand how waveforms will interact, how much out-of-band spectrum suppression is required to minimize interference between waveforms, how much guardband is required to avoid interference between adjacent users. Flexibility is needed to evaluate and research many different scenarios, both in simulation and also for an R&D testbed. A potential use case for the approach that's going to be shown in this webcast is to generate various interference scenarios where there is a desired signal as well as potential interferers and feed them into receiver hardware to investigate the impact to system performance. Now, using software to generate these different scenarios has a benefit of flexibility in being able to generate waveform types that might be difficult to generate with hardware. Several examples include candidate 5G waveforms, where the 5G hardware might not yet exist, or a satellite or radar signal in which the complex hardware systems are not readily available. In this next section, we'll provide a brief overview of some of the candidate 5G waveforms being proposed. There are many waveforms being researched for 5G applications, but let's just discuss a couple of the key candidate waveforms. The first one is OFDM, orthogonal frequency division multiplexing, is currently used in 4G, and for that reason and more, it's under consideration for 5G through the use of filtered OFDM. The second one is FBMC, or filter bank multi-carrier. FBMC applies filtering on a per subcarrier basis to provide improved out-of-band spectrum characteristics. It uses a flexible approach to baseband filtering using either a polyphase network or an extended IFFT filter. The third one is UFMC, or Universal Filtered Multicarrier. This scheme applies filtering on a per subband basis instead of a per subcarrier basis as with FBMC. One potential benefit of UFMC is reduced complexity of the baseband algorithms. So now let's take a closer look at each one of these. This slide shows how the steeper spectrum roll-off of some of the candidate 5G waveforms are related to spectrum efficiency. While OFDM has become a popular multi-carrier modulation scheme, it suffers from high side lobes that can threaten adjacent users. The simulation case study shows that the proposed new waveform technologies, FBMC, UFMC, and others, have good out-of-band performance, and thus may offer the potential for smaller frequency guard bands to achieve higher spectrum efficiency. So why is this important for coexistence? Out-of-band spectrum emissions can potentially impact the system performance of adjacent users. It may play into how efficiently available spectrum may be used and how many users could potentially utilize that available spectrum. That was a very brief overview of some of the candidate 5G waveforms and how their filtering characteristics can potentially improve spectrum efficiency. For additional detailed information on candidate 5G waveforms, please see the testbed white paper we'll reference at the end of this webcast. Now let's evaluate a coexistence case study with 5G candidate waveforms combined with 4G, 3G, and pan waveforms. Here is a picture of the flexible test bed, which will be used in the first coexistence case study. Here we're going to be generating signals below 5 GHz, so they will be generated directly from channels 1 and 2 of an M8190A arbitrary waveform generator. Channel 1 will be used to generate several different candidate 5G waveforms. Channel 2 will be used to generate legacy 3G, 4G, and pan waveforms. The two channels are combined together using an external splitter at the PXA signal analyzer's input. The composite signal is then analyzed using the 89600 VSA software with the PXA. So for the first case study, the 5G candidate waveform is an FBMC signal and the 4G waveform is an LTE signal. The LTE and FBMC signals are generated using a system view schematic, which is shown here. Now, if you're not familiar with system view, it is a system level simulator which can be used to quickly put together system level designs and evaluate design requirements and simulation. It can also be used to evaluate algorithms at a system level. So it lends itself towards early research activities such as 5G to evaluate design requirements and evaluate design trade-offs in simulation. System view also has connectivity to Keysight test equipment. So here we're using system view in our testbed to generate waveforms for our coexistence case study. The FBMC signal source and the LTE signal source are shown on the left side of the schematic. They generate complex waveforms that are then modulated onto carriers using IQ modulators. They are then fed into a signal combiner element, which resamples the two waveforms that have different sampling rates. It combines them into a single composite waveform that is then downloaded to an M8190 arbitrary waveform generator, or AWG. The output of the AWG is then analyzed using an N9030B PXA signal analyzer and the 89600 VSA software. One of the challenges with combining multiple types of waveforms is that they can have different center frequencies, different bandwidths, and different sampling rates. This can make it challenging and difficult to combine many different and disparate waveforms. Fortunately, recent breakthroughs in simulation arbitrary resampling technology has enabled multiple input signals with different center frequencies, different bandwidths, and different sample rates to be combined together. This is made possible with a signal combiner element, which effectively resamples multiple input signals and it combines them together to create one composite output waveform with a user-defined sampling rate, which can be set by the user for an arbitrary waveform generator. This makes it convenient to create complex waveforms in simulation, which can then be downloaded to an AWG to create coexistence test signals for the R&D lab environment. This shows the resulting test signals as measured with the PXA signal analyzer. Notice the sharp out-of-band spectrum roll-off of the FBMC spectrum compared to the LTE spectrum. This is due to the per subcarrier filtering applied to the FBMC signal that we had discussed previously. So to evaluate the coexistence of the LTE signal in the presence of the FBMC signal, the test scenario was modified in System View to notch out some of the active subcarriers in the FBMC signal. The LTE center frequency was then set so that it was centered in the notch. The upper right display shows the measurement result using the 89600 VSA software on the PXA signal analyzer. The LTE EVM is approximately 0.6%, which indicates that the FBMC out-of-band characteristics are having minimal impact on the LTE signal for this particular notch configuration. So now let's evaluate a broader scenario in which we'll vary the notch width to determine where it does start to have an impact to the LTE signal. Here we varied the FBMC notch width to evaluate LTE EVM as a function of decreasing FBMC notch width. LTE EVM is shown on the y-axis, and the FBMC notch width in terms of the number of subcarriers deactivated is shown on the x-axis. We can see that the LTE EVM is impacted as the FBMC notch width decreases, particularly when the FBMC notch is less than 70 subcarriers wide. This type of scenario could be useful in determining how much guard band is required for for coexistence between the two waveforms to maximize spectrum efficiency. Here we used LTE EVM as the metric for waveform quality and as a measure of the interference impact, although bit error rate, or BER, could be another metric of interest for a receiver. Another point to mention is that if the FBMC waveform were passed through a transmitter power amplifier or a PA that was in compression, the spectral regrowth of the FBMC signal might have an impact to the LTE coexistence. So let's take a look at how the RF impairments can change the waveform characteristics and correspondingly the coexistence. Here we've modified the system view schematic, which was used in the previous case study, to add a simulated transmitter design. The FBMC source produces an IF, which is bandpass filtered and upconverted to 2 GHz using a mixer and an LO. Then it's passed through a bandpass filter and a power amplifier, which has a 1 dB compression point to model the nonlinear power amplifier or PA characteristics. The LTE waveform and the FBMC waveform again are resampled and combined into one composite waveform. But here the composite waveform will be analyzed in simulation instead of downloading it to test equipment. The 89600 VSA software will be used in system view instead of with test equipment to evaluate the simulated coexistence. These are the simulation results for a case where the PA has a 1 dB compression point of 30 dBm. The blue trace on the spectrum plot on the left is the notched FBMC signal, and the red trace is the LTE signal. You'll notice that the spectral regrowth resulting from the simulated PA is filling the notch, and the notch depth is not as deep as what was shown in the previous case studies with test equipment. The demodulation of the simulated LTE signal also shows an EVM of 2.1%, resulting from the spectral regrowth in the FBMC notch. Let's take this a step further and reduce the PA 1 dB compression point to 27 dBm. Here we've reduced the PA 1 dB compression point from 30 dBm to 27 dBm. We can see more spectral regrowth in the FBMC notch, and the notch depth is shallower than when the PA 1 dB compression point was set to 30 dBm. We can see from the demodulation results that the LTE EVM has increased from 2.1% to 3.6% as a result of the FBMC interference within the notch. The PA RF impairments have impacted the coexistence between the FBMC waveform and the LTE waveform. So an interesting point to note here is that the baseband waveform performance for a candidate 5G waveforms being considered might actually be impacted by RF design performance. This is an important point for a system engineer to consider in trading off baseband waveform requirements versus RF design requirements. Effectively, the desired out-of-band performance of a candidate 5G baseband waveform could be eroded if the RF design performance isn't sufficient to preserve the baseband waveform characteristics. So now let's examine a more complex coexistence scenario. For this scenario, we will combine 4 different 5G candidate waveforms: FBMC, GFDM, OFDM, UF-OFDM or UFMC, and these will be combined together along with an LTE 4G legacy waveform using system view signal sources. Each of these have independent center frequencies, sample rates, and bandwidths, and are resampled and combined together into one composite waveform. The output center frequency for the signal combiner waveform is set to 2 GHz, and the output waveform sample rate is set to 1.2 GHz. This waveform is downloaded to the M8190 AWG channel 1 using the digital upconversion mode or DUC mode. This shows the resulting output spectrum from channel 1 of the AWG measured with the PXA signal analyzer. From left to right is the GFDM waveform, the notched FBMC waveform with the middle subcarriers notched, the LTE waveform centered in the middle of the notch, a custom OFDM waveform, and a UFMC waveform. So channel 1 of the AWG is playing the 5G candidate waveforms. So now let's take a look at channel 2. Channel 2 of the AWG will play the legacy 3G, 4G, and PAN waveforms. 6 different waveforms are being resampled and combined: LTE, Edge, GSM, WCDMA, Wireless LAN, and Zigbee. The LTE, Edge, GSM, and WCDMA waveforms use model and file-based sources in System View. However, the wireless LAN and Zigbee sources use the 89600 VSA source to read in recorded SDF files into System View. The 89600 VSA software can be used with test equipment to capture real-world recordings or SDF files, and those recordings can be read into System View. MATLAB code can also be co-simulated in System View, so this approach offers the flexibility of combining many different types of signals together in simulation and resampling them to combine them together to download a composite waveform to the M8190A AWG. The output center frequency for the signal combiner waveform is set to 2.2 GHz, and the output waveform sample rate is set to 1.2 GHz. The waveform is downloaded to the M8190 AWG channel 2 using the duck mode. This shows the resulting output spectrum from channel 2 of the AWG measured with a PXA signal analyzer. Here we're zooming into a portion of the spectrum with the LTE, Edge, GSM, and WCDMA waveforms. Wireless LAN and Zigbee are not shown for this frequency span setting. So here channel 1 of the AWG is playing the 5G candidate waveforms, and channel 2 is playing the legacy 3G, 4G, and PAN waveforms. The two channels of the AWG are combined together with an external splitter. The resulting spectrum, as measured with the PXA signal analyzer, is shown here. Again, wireless LAN and Zigbee are not shown for this frequency span setting. For this example, we decided to download the 5G candidate waveforms to channel 1 of the AWG and download the legacy 3G, 4G PAN waveforms to channel 2 of the AWG. However, they could have been combined together in one waveform to download to a single channel. Multiple M8190A AWG blades can be used if additional channels are needed, so this approach is scalable and it's flexible. The 89600 VSA software can be used on the PXA signal analyzer to tune into each waveform to perform the demodulation and measure the EVM. Here we can see that the measured EVMs are quite low, even though we're generating composite waveforms with many different types of signals on one AWG waveform. We're demodulating each waveform using the multi-standard radio capability on the 89600 VSA software. GSM is shown on the left, followed by Edge, an LTE signal at 1.9 GHz, followed by an LTE signal at 2 GHz, which is parked in the FBMC notch, followed by WCDMA on the right. The center frequencies, bandwidths, and other waveform characteristics are parameterized, so the signal scenario can easily be modified to evaluate many different scenarios in the R&D lab environment. Customized parameters were defined for this application example, which enable parameters such as carrier frequency, relative signal power, sample rate, oversampling, and other parameters to be varied and set to define different signal scenarios. This is easily customizable by the user in System View. Now let's move beyond sub-6 GHz and into centimeter waves. Centimeter wave frequencies are of interest for 5G high data throughput applications, and shared spectrum usage is being proposed and investigated for the 28 GHz frequency band. So now let's see how the testbed setup can be scaled to evaluate potential coexistence issues between satellite waveforms and candidate 5G waveforms. This is the test setup which will be used for these case studies. To generate the wideband 28 GHz satellite and 5G candidate test signals, an E8267D vector PSG with wideband IQ inputs has been added to the M8190 AWG, essentially scaling up the test setup. Here the M8190 AWG will be generating I and Q, which is then modulated on to an approximate 28 GHz carrier frequency using the PSG. This combination of the M8190A AWG and PSG can generate test signals up to 44 GHz with up to 2 GHz of modulation bandwidth. The test signals are analyzed using either an N9040B 50 GHz UXA with 1 GHz of bandwidth or with a 33 GHz oscilloscope. Shared spectrum usage is being proposed and investigated for the 28 GHz frequency band. To generate the test scenarios for our 28 GHz case study, system view is being used to generate a wideband satellite waveform and a wideband candidate 5G waveform. Note that in this case, the candidate 5G waveform is a custom OFDM waveform. Now these are resampled, they're combined into one composite waveform, which is downloaded to the M8190A AWG. The I and Q waveforms from the M8190A AWG are fed into the PSG wideband IQ inputs to modulate the IQ waveforms onto the approximate 28 GHz carrier. The resulting spectrum with the candidate 5G waveform and wideband satellite waveform is shown on the right. For this scenario, the candidate 5G custom OFDM waveform and the satellite waveform are coexisting. The demodulation of the custom OFDM waveform with 89600 VSA software on the oscilloscope is shown on the right. The constellation looks reasonably well, so the two waveforms are coexisting for this scenario. Now let's take a look at a second scenario. Here we've changed the test scenario by moving the satellite signal closer to the candidate 5G custom OFDM signal. Looking at the 89600 VSA demodulation results, we can clearly see that there's poor coexistence between the candidate 5G waveform and the satellite waveform. The constellation shows significant dispersion as a result of the satellite signal interfering with it. The spectrum shows the satellite signal encroaching on the candidate 5G signal. This can also be seen on the VSA spectrum. Let's now take a closer look at how this impacts EVM versus subcarrier. On the left VSA display, the EVM versus subcarrier on the upper right shows the impact of the satellite signal, especially on the subcarriers near the band edge. The EVM result on the lower right corner of the left display shows a much higher EVM, indicating that there is poor coexistence between the candidate 5G custom OFDM waveform and the satellite waveform for this scenario. This EVM number is an average across the entire acquisition time and bandwidth of a signal, but the VSA software can provide a breakdown of errors versus frequency or subcarrier, or errors versus time or symbols. Now on the VSA display to the right, we've zoomed into the subcarriers impacted by the satellite interferer. The white trace is the average EVM versus subcarrier. We can clearly see that it ticks up at the band edge where the satellite signal is interfering with the candidate 5G OFDM signal. The blue and green vertical lines represent the distribution of EVM results at each subcarrier versus symbol. Shared spectrum usage may also potentially be of interest in the 39 GHz frequency band. Here's a different test scenario at 39 GHz generated with the same test setup, since the PSG can cover frequencies up to 44 GHz. The software is the key to generating new coexistence scenarios. So here, a system view has been modified to generate a multi-carrier satellite signal instead of a wideband satellite signal. The candidate 5G waveform remains unchanged relative to the previous coexistence scenario. For the multi-carrier signal, each carrier is configured to be either a QPSK, 8 PSK, or a 16 QAM waveform. Let's now switch gears and examine how a similar approach can be used for a radar LTE coexistence case study. Then we'll return to 5G and discuss millimeter wave applications. There is interest in proposed future spectrum sharing between radar and LTE. It poses questions, however, such as when a ship approaches land, how will the radar system interact with LTE? Conversely, how will the LTE signal interact with the radar system? Also, how about a Coexistence scenario, where an LTE system is in close proximity to a radar system? Modern electronic systems operate in an increasingly complex spectral environment, competing for available bandwidth. So for example, Navy ships must deal with a myriad of electronic systems, including radar and communication systems, which potentially could interfere with each other. The US Navy is also investigating ship-based LTE for close quarter communications, adding even more complexity to these spectral environments. Investigating potential interference issues between complex wireless signals such as LTE and radar may be useful to ensure successful deployment. So let's see how the coexistence testbed we used for 5G, 4G, 3G, PAN, and satellite coexistence can be applied for these types of applications. Here's a picture of the flexible testbed which is used for this coexistence case study. It's effectively a similar test setup to what was shown for the 5G coexistence case studies, but here we're using the SystemView radar library instead of the SystemView 5G library. We're also using a PXA signal analyzer instead of a UXA signal analyzer, but either one could be used. For this example, we'll evaluate coexistence between an S-band radar and an LTE emitter within a multi-emitter spectral environment. The S-band radar emitter is shown on the top left, followed by an LTE downlink, edge, GSM, and WCMA emitter. An additional S-band radar and WCMA emitter are also shown. A wireless LAN recording was captured using the VSA software and is read into the simulation environment as a simulation signal source. Note that although the wires look like they're disconnected, they are actually named nodes connecting each signal source to an input bus on the signal combiner element. The multi-emitter spectrum is shown here. Again, this included a GSM, edge, and LTE emitter, as well as 2 S-band radar emitters and 2 WCMA emitters. The LTE and S-band radar emitter are shown near the center of the measured frequency spectrum. The PXA is used to measure the spectrum and EVM performance to evaluate the coexistence between the LTE and radar emitter. So here we're zooming into the portion of the multi-emitter spectral environment which contains the LTE and radar emitters. The VSA demodulation results show the constellation, spectrum, EVM versus subcarrier, and EVM error summary. You can see that the radar emitter has some impact on the LTE performance in this scenario. The EVM is approximately 1.3% in the presence of the radar emitter, and the EVM versus subcarrier measurement shows performance degradation resulting from the radar interferer. For the second scenario, the radar emitter was moved closer to the LTE emitter, as shown here. The simulation was rerun to create the new test signal. In this case, the radar emitter has significant impact on the LTE performance relative to the first scenario. The EVM has degraded to approximately 14.1% as a result of more spectral overlap with the radar spectrum. The EVM versus subcarrier measurement also shows additional performance degradation resulting from the radar interferer relative to the first scenario. So we've looked at coexistence impact in terms of EVM, which is a key transmitter metric. Now let's take a look at coexistence in terms of bit error rate. Bit error rate and throughput can be key metrics for receiver sensitivity, both with and without interferers present. This part of the case study utilizes simulation schematic shown here to evaluate the impact of an S-band radar interferer on simulated LTE downlink coded bit error rate, as the interferer's center frequency is swept. The schematic consists of an LTE downlink signal source. Below the LTE signal source is an LFM chirped radar signal source. The center frequency of the LFM chirped radar is swept for the bit error rate simulation. The LTE signal and the radar signal are combined together, then they are fed into the LTE receiver for the coded bit error rate simulation measurement. This shows the coded bit error rate simulation results as a function of the radar interferer center frequency, which was swept in the simulation. The LTE coded bit error rate performance is significantly impacted as the radar interferer center frequency is swept across the LTE downlink frequency, increasing from 0% bit error rate to approximately 24% bit error rate. Now let's switch back to 5G and millimeter waves. Before we wrap up, we'd like to switch gears back to 5G and interject one last topic. Throughout this presentation, we've discussed potential coexistence issues in spectrum sharing, where the interference between signals is a key concern. Millimeter waves are also a research area for 5G and may offer some potential benefit in mitigating interference by using highly directional links. It may also offer a potential benefit in spectral reuse due to the propagation losses at these high frequencies. In this test setup, we were generating and analyzing a millimeter wave signal at 73.5 GHz with 5 GHz of occupied bandwidth. This was a demo which we performed at IMS 2016 in San Francisco. The millimeter wave link was highly directional, So any slight misalignment between the transmit horn antenna and the receive horn antenna resulted in the loss of signal energy and impacted the EVM performance of the link, as shown on the video on the right. The directional nature of millimeter wave links may be useful in helping to mitigate interference effects, while potentially utilizing more spectrum for high data throughput applications. In summary, we started the presentation discussing the already crowded sub-6 GHz spectrum. New 5G candidate waveforms are being researched, and potential future spectrum sharing between satellite and 5G, as well as radar and LTE, are being considered. Coexistence between these new and legacy waveforms will be important moving forward to ensure that system performance is maintained. In this webcast presentation, we discussed a flexible testbed, which can be used to evaluate many potential coexistence scenarios for 5G, wireless, satellite, and radar applications in the R&D lab environment. While an R&D testbed approach is key for R&D applications to help gain insight into potential coexistence issues which may be difficult to replicate in the field, it does not replace field testing with actual hardware. We examined several different case studies during this webcast which illustrated the flexibility of this approach using software-defined waveforms. This new white paper can be downloaded for more information on Keysight's flexible testbed for 5G waveform generation and analysis. This also covers centimeter wave and millimeter wave applications for 5G, in addition to sub-6 GHz applications. This application note can also be downloaded for more information on evaluating coexistence between radar and wireless emitters. We had also discussed how cognitive radio approaches might be investigated for potential increased spectrum utilization with dynamic spectrum sharing. This white paper discusses a flexible testbed which can be used for cognitive radio applications. Please visit our website or contact your local Keysight representative for more information on Keysight's 5G waveform generation and analysis testbed. There are additional resources available at this website, such as demo videos and more. Thank you for attending the webcast. I hope you found this presentation interesting and informative.